Good day everyone. I am Soumya from the Department of Artificial Intelligence and Data Science. Today we are going to explore a fundamental concept in verifying the software correctness, that's of model checking. Model checking is an automated technique that has become the critical in modern software engineering, especially for systems where correctness and safety are non-negotiable, such as embedded systems, protocols and safety critical applications. As our software systems grows increasingly, object-oriented and concurrent formal verification methods like model checking help us to rigorously validate the behavior against the specification. Then, what is model checking? Let's define model checking. It's an automated verification technique used to check whether a given system model meets the certain desired properties such as safety and liveness by exploring all possible states the system can enter. It answers a powerful question of, does my system always behave correctly under all possible inputs and states? This is especially useful in detecting the subtle bugs that are hard to catch through traditional testing or code reviews. Unlike testing, which samples the behaviors, model checking exhaustively exposes the all executions path. Then, how model checking works. Here is how the model checking process typically works. First one is of model creation. You first abstract your system as a model, typically a finite state machine. These models represent the states, for example, of logged in and transaction pending, and the transitions of how you go from one state to another. Then second one is property specification. Next, you define what the system should or shouldn't do. For examples of, the system should never crash, an elevator door should never open while moving. These rules are often written in temporal logic like LTL. LTL is for nothing but linear temporal logic, or CTL, computational tree logic. Then third one is of running the checker. A model checker tool like SPIN and NUSMV or UPPAL analyzes the state space to verify whether all possible paths adhere to these rules. Then fourth one is counter examples. If a rule is violated, the tool gives a counter example of a path through the system that leads to failure. This is extremely helpful for debugging. Now, a real life example of traffic light system. Let's understand this using a real world system of traffic light controller. The states here are red, green and yellow. The system must follow the cycle of red, green, yellow and red. Now, what if there is a bug that lets the light go directly from red to yellow and skipping the green color? This could cause a traffic accident. With model checking, we model the system as a finite state machine. And here we define the properties such as green should always follow the red color and run a model checker to systematically verify the behavior across all transitions. If the skip exists, the tool flags it with a counter example. Then, how model checking applies here. These slides shows how we translate the traffic light into a formal model. Here we states are red, green and yellow and the transitions are here are red, green, yellow then red. We specify the constraints such as never go red to yellow directly. Never skip any state in the cycle. The model checker simulates every possible transition path, even those we might not think to test manually. It will raise an alert if an illegal transition is possible under any circumstances. In object-oriented software engineering, now let's connect model checking to object-oriented software. In object-oriented programming system, behavior is represented through object and classes. Then state changes, for example of changing the login status of a user. Then interaction between the components, for example of users logs in, places order and gets a notification. These interaction can be modeled as state machines. For example of, a user must log in before placing an order. A payment should not be processed unless the code is confirmed. Model checking helps to ensure that object behavior doesn't violate such constraints, especially in complex event-driven applications. It allows developers to verify the logic before deployment and reducing the bugs in production. Then, benefits of model checking. Model checking offers several powerful benefits. Automation. Once your model and properties are set, the analysis is completely automated here. Then early detection. You can find subtle logic errors before the software is even deployed here. Then counter example generation. You don't just know something went go wrong. You get an exact scenario that leads to the issue. Then thoroughness. Unlike testing, model checking exhaustively verifies all possible inputs and states. Then integration. It can be used alongside traditional testing to create a formally verified software pipeline. Then limitations of model checking. While model checking is powerful, it's not without its challenges. First one is of a state explosion problem. As system grows, the number of possible states increases exponentially. These can make model checking computationally expensive. Then abstraction required. Real world software must often be simplified into abstract models. These may omit the important behaviors if not done carefully. Then tool limitation. Some tools are hard to use or limited to certain types of models. For example, a finite state only. Then learning curve. Engineers need to learn modeling formalisms like state machines and temporal logic. Despite this, model checking remains an indispensable technique in formal verification, especially software correctness is important, such as in medical, aerospace, and financial system. To conclude, model checking is a rigorous verification tool that ensures your system works correctly in all scenarios. It is especially useful in safety critical and object oriented system. While not a replacement for testing, it provides a mathematical confidence in your software correctness. I encourage all future software engineers to learn at least the basics of this technique. It's a key part of building the reliable, trustworthy systems. Thank you.